Well, it's a wild Friday night here at the Miller household, and dinner's just been completed, and what better after dinner than a bit of the bisection method. So today what we're going to look at is a method for approximating the x-intercepts, the roots, the zeros, whatever you want to call them, of, at this stage, just polynomials. So the example that we did in class was this one here, f of x equals x cubed, take x, take 1, and what we want to do is find an approximation for the solution for it, and the question's telling us that the solution happens somewhere between 1 and 2, and they want this to an accuracy of 2 decimal places. So obviously the solution to this is not an integer, so it's something we can't easily factorize and generate the solutions. So the thing I think we should do first is actually have a look at what this function looks like. So let's put it into Geogebra. F of x equals x cubed, take x, take 1. And they're not sending us on a wild goose chase, because between 1 and 2 is the x-intercept. So there is the actual x-intercept there, and it falls between 1 and 2. Now, as a guessing person, that's 1.5 there. I can see that the solution is roughly 1.3. Okay, so that's, just the visual approximation, but again, we want to be a little bit more precise than this. So the next step is, because this is going to be a CAS-based question, is why don't we actually get the solution? So what I'm going to do is use my solve function, and I'm going to solve the function x cubed, take away x, take away 1, when y is equal to 0 for x. And we want to be in decimal mode because we're going to get an approximation of the solution. And of course the approximation is 1.3247 blah blah blah, to 2 decimal places 1.32. So I actually already know the answer. Okay, the approximate solution to this with an accuracy of 2 decimal places is 1.32. Now, why is this table sitting here? Well, I suppose the burning question is, and this might have kept you up sometimes at night, how did they get this approximation? How would the calculator work out that the solution is roughly 1.324 blah blah blah? Well, one possible method, and I don't know whether this is the method the calculator uses, heaps of different ways to get it, could be the bisection method. So essentially what we'd be doing with the bisection method is trying to find out an approximation for this x-intercept here. Okay, now essentially the way it works is as follows. I'm just going to use this bit of blank bit of paper here up above me to try and demonstrate. Just say we've got this straight line here between these two ends. I'm looking for this cross. Well, logically you think, if I'm looking for the cross, the way I'll do it is I'll just go find it. But if we're a computer, or we're trying to generate an algorithm that covers all varieties or permutations of this problem here, one method to do it is actually, if I'm looking for this cross here, is I go half the distance between the endpoints, which is here. I work out which side the cross is on, which is in this case this side. Now I can forget about this side, it's not there. And I concentrate on looking between here and here. So what I do is I find the midpoint between this and this, which is roughly here, and I work out which side it's on, and in this case it's on this side. So I forget about this, and notice what's happening here is I'm getting closer and closer and closer to where the cross is. So I'm looking between here and here, I find the midpoint, I find that the cross is on this side, so I can get rid of this. Midpoint of this and this goes, midpoint of this and this, and I'm getting really close now. Okay, so essentially that's the method the bisection method uses, or that's the way the bisection method actually tries to hone in on the root or the zero or the x-intercept or whatever you want to call it. Okay, so what this gives us, and this table down here gives us, is a more systematic way of working it out. Okay, so the first step says here, before you start, define the function in your calculator and evaluate the value of the function at the two endpoints. Okay, so let's do that. We're going to define, and remember I can type that in because I've got an actual keyboard, but it's going to be in Math 3, and we're defining f of, in this case, x, not f of y, equals x cubed take x take 1. Alright, now what we're going to do is evaluate f of 1, and all we're going to note at this stage is actually whether it's negative or positive. Okay, so we're not too worried about y, or what the value of f of x is when x is 1, we're just worried about whether it's negative or positive. So I'm just going to note down in my table here that f of 1 is negative. And I'm going to do f of 2, and I'm going to note that that is positive. Now that's what needs to happen. Okay, we need to be negative and positive, or positive and negative on the endpoints, because what that will mean, and I'll try to explain by again looking at the graph over here, is that we are on either side of the x-intercept. So when I did f of 1, it told me that the y value was negative 1. Okay? If I did f of 2, or when I did f of 2, it told me that the answer was 5, right, which is here. Right, so it was positive on this side and negative on this side. So that means we're looking in the right spot. Okay? Now what happens is if it's positive and positive, for example, if I was looking between 1.5 and 2, I've lost it. Okay, because they're both going to turn out positive. Okay, so f of 1.5 is positive and f of 2 is positive. So that means I've actually lost it, or I'm looking on the wrong side. Okay. Alright, so now that we've worked that out, what we can do is calculate the midpoint of 1 and 2. Right, and essentially the reason we're doing that is we're deciding which side the x-intercept is on. Is it on or between 1.5, or is it between 1.5 and 2? So let's calculate the midpoint. The midpoint is found by doing 1 plus 2 and then dividing the result by 2. So our midpoint is 1.5. And then what we're going to do is get f of the midpoint, which in this case is 1.5. Now again, all I'm noting at this point here is whether the midpoint is positive or negative. So we note here that the midpoint produces a positive y value. So now this is where we have to make a decision, and really doing the bisection method involves lots and lots of decision making. That's really the hardest part to it. Alright, what I need to make sure at this stage is that I'm on either side of the x-intercept. Now what has to happen is, if I know I'm on either side of the x-intercept when I've got opposing signs, negative and positive, or positive and negative. So at this stage here, my midpoint is positive, 2 is positive, so it can't be between 1.5 and 2. Now 1 is negative, 1.5 is positive, so it's actually between 1 and 1.5, and we already know this because we do know the answer. We know the answer is 1.32. Alright, so what I'm going to do is restate my interval now. Now I'm not looking between 1 and 2, I'm looking between 1 and 1.5. So my left endpoint is 1, which we know at this stage is negative. My right endpoint is 1.5, which we know is positive. And what now we're going to do is calculate the midpoint of this. So we're going to go onto our calculator again, and again this is a really CAS or tech active type problem. 1.5 divided by 2, and we're going to do f of 1.25, so f of the answer. Right, so what we note is that the midpoint is 1.25, and the y value when x is this value here is negative. Alright, so again it's decision time, okay, because what we're trying to work out is, where is it? Is it between 1 and 1.5, or is it between, is it between 1 and 1.25, or is it between 1.25 and 1.5? And what we know is this and these signs here oppose each other, so I know it must be between 1.25 1.25 and 1.5. So I'm going to restate my interval now, which is saying that it's between 1.25 and 1.5. We're going to write our left endpoint, write our right endpoint. We know that our left endpoint here produced a negative value, so this is going to be negative. And our right endpoint, we know from the last time round, was positive. So this confirms we are looking in the right spot. Remember, if you write this line down here and it turns out positive, positive, or negative, negative, you know you've lost it. Okay, it's somewhere you've chosen the wrong side at some point. So once again, what we're going to do is try to hone in further on the midpoint. So you can see here, our approximation at this stage is 1.25, or it's between 1.25 and 1.5. So we're getting closer. So we're going to do 1.25 plus 1.5, divide the result by 2, and note that the midpoint is 1.375. And then we're going to find f of the midpoint. We're going to find out what y is when x is 0. Now you notice these y values that we're producing are also getting smaller and smaller. That's because we're getting closer and closer to here. And when we do f of these x values here, it produces a smaller and smaller y value, and that's a good sign. It means we're getting closer and closer and closer. Alright, so what that did was produced a positive. Okay, so what I know now is that our approximate solution, or the root, must be between 1.25 and 1.375. And again, I know this because I also have already done the approximation. Alright, so it's going to be between 1.25 and 1.375. So again, you can see that we're getting closer. 1.25 produced a negative y value, 1.375 produced, as we can see here, a positive y value. Right, so again, you can see it's fairly algorithmic in nature. All we're going to do now is add these two numbers together. Divided by 2, 1.3125, and we're going to f of the answer, and we're going to note that that produces a negative. Alright, so now again it's decision time as we work out where is this thing, okay, and we note that this is the negative, this is the positive, it must be between here and here. So we're going to write down those values, with the lower value being the left, or becoming the left endpoint, 1.3125 and 1.375. So again, you can see that we're getting closer and closer to this approximation here that the calculator does. Alright, now 1.3125 produced, that was this one here, produced a negative, and 1.375 produced a positive. Alright, so again what we're going to do is find the midpoint, 1.3125 plus 1.375. Divide that by 2 and find f of the answer, or find the y value when x is the midpoint. So our midpoint, we'll just note that down, is 1.34375, and that produced a positive midpoint. Alright, just pausing there to have a couple of sips of my cup of tea here, because the bisection method is certainly thirsty work. It's the equivalent, I think, in maths of, you know, running the marathon, really. So anyway, let's keep pounding away at this, because again, what I'm targeting is getting to 1.32, and you can see here I'm getting closer and closer. Alright, so what we're going to do is we are deciding that the x-intercept is between this value here and this value here, because this turned out positive. So let's write up what our endpoints are. 1.3125 and 1.34375. Okay, now we know that 1.3125 turned out to be negative, and 1.34375 was positive. Again, we need this check to make sure that we are in the right spot. Now what we're going to do is again calculate the midpoint. So as much as possible, use stuff that you've already typed into the calculator, because it saves you from maybe doing a data entry error. So our midpoint is now 1.328125, and if I calculate f of the answer, it's turned out positive. Why is that hand there? I'm just going to have to pause this again to get rid of that. Alright, so that turned out positive, so we're just going to note that it was positive. And we're also noting here in the calculator that the y value produced is getting really low. Okay, it's gone from -1 over here and 5 over here to, getting really close to 0. And again, that means we're getting really close. Okay, it's producing really low y values, which means that the further or the closer we get to the actual x-intercept, or the really good approximation of it, the closer the y value should be to 0. Because what's the value of y when x at the x-intercept? The value of y is actually 0. Okay, so let's go through it on this. It's between 1.3125 and 1.32825. So 1.3125, 1.328125. 1.3125 was neg. 1.328125 was pos. And now we're going to grab the midpoint. So it's between this value here and this value here. So again, I'm just trying to recycle old values that I've already typed into the calculator. 1.320325. Now we're going to check out what y is when x is that value. So f of the answer, and it's negative. Okay, so it's suggesting, of course, that it's between this and this. So we're going to go 1.3203125. The numbers are starting to get really big now. Not big, but number of decimal places. 328125. Okay, so this is just confirming that we're on either side. And we were looking for an approximation that would equal 1.32. Now, why can't we call it quits here? Well, the left endpoint says that the answer is at this stage 1.32. The right endpoint suggests that the answer is 1.32 with an 8 here, which means at 2 decimal places it rounds to 1.33. So our answer still, according to the bisection method, could be 1.32 or 1.33 to 2 decimal places, remembering that we don't really know that this is the best approximation in theory just yet. Okay, so what we need to do is we need to keep going until this value here either goes 5 or more, or this value here, the 8, goes less than 5. Okay, and that will get us a definitive round. Now, I'm not going to keep going on this, because one thing is that the numbers are going to get bigger and bigger and bigger. So what I'm going to do is show you, or pull up a document with it worked through to when you will be able to find that out. So I'll do that now. Alright, so what we've got here is a spreadsheet showing electronically what we were working out by hand here. Okay, so these are the values that I worked out by hand, and you can see here that these are the same values that I was producing. And so what we're noting here is that this one here, or this line here, represents the first pass through. So we're just going to note these down. 1, 2, 3, 4, 5, 6, 7, 8. So I've made 8 passes or 8 executions through the algorithm to get down to this point here. Okay. Now if we look here, these will be the exact same values. 1.3. So the lower bound was 1.320. The upper bound was 1.328. Okay. Now let's actually examine what happens on the 9th, 10th, 11th, 12th and 13th pass. So on the 9th pass it came up as 4 and 8. Okay, so that didn't get us, or didn't help us out too much. And I remember doing that in class, and the girls were starting to really moan and groan at this point as they were sort of going and willing the algorithm to choose or find a number either below 5 or 5 and over. On the 10th pass it was 4 and 6, so that didn't help us. The 11th was 4 and 5. The 12th was 4 and 5, so still no definitive answer. But here it is on the 13th, 4 and 4. Okay, and so now the rounding on the left end point and the right end point would both round to 1.32, so we can lock in our approximation as 1.32. So this would have taken you 13 passes through the algorithm, or 13 executions of the algorithm, to find out the approximation. So with this method of approximating the x-intercept, it really is just practicing this idea here. Okay, you know, I don't foresee an exam, especially at Year 12 level, getting you to do a number of these executions. I could see something that we do in class on, say, an applied task, definitely doing something like this. I could see in Year 11 perhaps what we would do is maybe lop out a couple of lines, maybe remove this line here or remove this line here, and ask you guys to fill in, you know, the grey line or something like that for a couple of marks. So that's how I foresee it being assessed. Okay, and again, to reiterate that I realise a very quick way of approximating the solution is to quickly do a solve. Okay, so I realise that this is a very easy way to get a 2 decimal place approximation. So again, to reiterate, why are we doing this method here? Well, I suppose it gives us an appreciation of what the calculator actually does to get this solution. So in effect, we're being the calculator here, applying the algorithm and trying to get this approximation.